Okay, hopefully yesterday wasn't too difficult for anybody. We had the 3 lessons that we went over, and that's kind of going to be our pace. We're going to try to cover 3 lessons per day in class. And again, my goal is to cover all of those so you have no extra videos that you have to watch. Hi, Mama Davis. Maddie, tell her hello. All right. So moving forward here again, so we're going to second semester of Algebra 2. Right, again, we're covering 3 units. So today we're going to try to cover lesson 1.4 to 1.6. And again, if you can keep up with these 3 a day, then we're going to be finished with everything within the 3 weeks. Okay, so that's why we're pushing the pace, is to finish within 3 weeks. So that solo week you have limited to no work. Okay. So if we look at the first lesson we have to do today. So if we look at the first lesson we're doing today, it is on multiplying and dividing rational expressions, okay? So if we jump straight into it, okay, you're going to find out that multiplying and dividing rational expressions are going to be very similar to what we already do with fractions, okay? And again, that's kind of been the nature of this entire section, is we already have these tools in our tool belt, but now we just have to modify them and look slightly different. So just a reminder here that when you multiply fractions, right, when you multiply fractions, you just multiply directly across. So if we look here, we've got A over B and C over D. So when you multiply them across, you just get A times C over B times D. So looking at a couple of these problems here, at the top here, you've got 1 and 2. So obviously you multiply those together, you get 2, and then 3 times 5, that gives us 15. And then we've got 2 tenths multiplied by 5/6, that gives us 10 over 60, right? And obviously here, if we got this answer of 10 over 60, we could simplify further, obviously, to 1/6, right? Because we could divide both of those by 10. We could simplify this further. So obviously don't, if this is one of your questions, don't get confused if it says 1/6. So you might have to do the math first, and then you might have to simplify after. But you're going to do the exact same thing with rational expressions here, all right? You're going to do the same thing with rational expressions, which means you're still multiplying the top 2 together and the bottom 2 together. So if we look here at 1 over x and 2 over x plus 1. Okay, so we start with the original problem, and then we multiply the 2 top numbers and the 2 denominators, right? So 1 times 2 multiplied by x times x plus 1. All right, and again, being really, really careful that if you have a binomial or trinomial, right, you have to put those parentheses and distribute the value accordingly. So since this is an x plus 1, we distribute both of those x values. So this becomes x squared plus x in the denominator, and we have 2 on top. So our final answer there is 2x squared plus x. Right, and again, it says simplify. So that was our simplifying. We multiplied them together. We added like terms, and then again, if we can simplify further, we do. All right, so here's a couple more examples for you, especially if that sliding tool doesn't work. So again, if we go to maybe example 2 here, we start off with our 2 expressions. We combine them together so we can multiply the 2 numerators and the 2 denominators, right? The top one's not too difficult, right? It's just 1 value multiplied by 1 value. But remember, with the bottom 2, we have to FOIL that out. So we FOIL it out, we combine like terms, and at the end of it, we are left with this 5x squared over x squared minus 5x minus 14. So again, simplifying as we can. All right. Now we have something that, what if it's a complicated product? Okay, so it says complicated product. So again, something maybe not as simple as a 1 by 2. So we'll multiply them together, right? So they draw it with a straight line there. Obviously for the top, we know we're gonna FOIL, and for the bottom, we're gonna distribute out when we simplify. All right, so again, we have to FOIL, first, outer, inner, last on the top values, and then we will distribute on the bottom. All right. And then obviously if we have any like terms, we combine the like terms as we can. On the top and on the bottom, we combine the like terms if possible, and then we simplify. All right, so again, hopefully not too terribly difficult here. Again, it's processes you already know, but now applying it to something slightly different. All right, so again, looking at multiplying rational expressions, it's just like multiplying numerical fractions. All right, so to multiply two rational expressions, you have to multiply the numerators and the denominators together, right? So multiply the two tops together and multiply the two bottoms together. And if we look at the steps for how to do this, okay, pretty simple. Multiply the top, multiply the bottom, and what it showed was combine them, multiply, and simplify. All right, so if we look at maybe one or two of these problems here, just so that you can have some. Again, you're going to multiply the top two together and multiply the bottom two together. So 4 times 2 on top. So immediately we know the answer is going to have an 8 on top. So it's either going to be C or B. B or C there. All right. Then when we look at multiplying the bottom two together, we've got 5x times by x and 5x times by -1. So we should be left with the 5x squared, which both of those have, but then we have to also multiply 5x times by -1. So our answer there is going to be B. All right, our answer is going to be B. And I know that when I do these problems, I don't obviously write them down, because when I write them down, it doesn't look very good for you all using that annotate tool. But what I would really suggest is make sure that you do all of these problems. Actually try to write them out on paper, because when you get to something like this might not be as obvious that it boils down to choice D there. All right, it might not be as obvious, but if we were to FOIL, let me try to see if I can draw this for you here. So if I was to FOIL first, outer, inner, and last. All right, so if I was to do this, this would end up with an x squared plus 2x minus 2x minus 4 on top, right? That would end up with that on top, so those plus and minus 2x would cancel out. And then if I did the same thing on the bottom, I would end up with an x squared plus 7x minus 7x minus 49, right? So again, making sure that you're writing down these steps and trying the math as you go is going to be really, really important for you, okay? Especially, again, something like this, where the bottom is most likely going to be a trinomial, right? You want to make sure that you don't get lost in the math there. So again, when you're doing these, make sure you are writing them out and following along with the process here. All right. But if we look at this first one here, okay, find the product of the two fractions. So clearly we multiply the top, we multiply the bottom. So this is going to end up with 3/10 there. 3/10, because 1 times 3 gives us 3, and then 2 times 5 gives us 10. All right. For number 2 here, find the product of the rational expression in the box below. Okay, so that's going to end up with a 6 on top. And then if I distribute this x, it's going to be x squared plus x. So I should have 6 over x squared plus x. All right. 6 over x squared plus x. And then for number 3 here, again, not as obvious, not as nice. Okay, so you would have to distribute. You would have to distribute that out. So I've got 2x times by x, so that's going to give me a 2x squared on top. All right, I've got 2x squared on top. Then I've got 2x times by 4. or negative 4. So my top should look like 2x squared minus 8x. So far, A looks like the right answer. But again, we got to make sure that it doesn't simplify out further. All right. And when I do my bottom, I end up with an x squared minus 4. So no, there's nothing that I can take out. So the answer there would be A. And by take out, what I mean is if there was if this ended up being, if our answer ended up being 2x squared minus 8x over 2x squared minus 4. Well, obviously, we could simplify that and take out a 2 from every value. So we would have x squared minus 4x over x squared minus 2, right? We could take out a 2 from everything if that was possible. But since our final answer doesn't have a 2 in everything, we don't simplify that down any further. Right, so our final answer there will be A. And then finally, looking at this one here, okay? And this ends up with x squared on top and x squared minus 4 on bottom. All right, so, oh, sorry. That ends up with an x squared on top and a 2x squared on bottom. Oh, I'm sorry, x squared minus 4 on bottom. All right. All right, so then we're going to apply the same principle than we do for fractions with rational expressions. So just to remind us here of what we do for fractions. Okay, if we're going to take 2/7 and divide it by 3/4, right? It says convert, but what it means is we flip that second fraction or take the reciprocal of it, right? So we flip that fraction and we actually multiply. So when we're dividing by this second fraction, the way that we can do it easily mathematically is we flip it and we end up multiplying. So it looks like 2/7 multiplied by 4/3. Okay, multiplied by 4/3. Okay, so when you divide by a fraction, you end up multiplying by its reciprocal. All right. So when we multiply that together, then it's just the same process, right? We take 2 times 4 over 7 times 3, so that gives us 8/21. And if we can simplify down further, we absolutely do. All right, so another example of showing it in brief, right, with letters is if I've got A divided by B, or sorry, A over B, and I'm dividing that by C over D, it really looks like A over B times D over C, right? I flip that second one and I end up multiplying, right? So I'm left with AD over BC, right? I'm left with AD over BC, okay? So looking at a couple of examples here. I've got 2/1 divided by 4/1. So what I do is I take that second one there, I flip it or take the reciprocal of it. So I've got 2/1 multiplied by 1/4. So I'm left with obviously 2/4. And then again, if we can simplify this down further, this one we could. So this answer 2/4 could also be written as 1/2 or 1/2. Okay. To look at maybe one more example, right underneath it, 2/5, if we divide by 5/6, it's like multiplying by the reciprocal. So we multiply by 6/5 instead, and we're left with 12/50. All right. So again, we're going to use this exact same principle for rational expressions. All right. So remembering that we have to flip the second and multiply, we're going to keep that same process. So if we have 2 over x, and we multiply by x plus 1, okay? And we multiply by, we end up multiplying by the reciprocal there. So we take it, we flip it. Okay, so we flip that second fraction and we end up multiplying by the reciprocal. Okay, and then we combine just like we did in the last step. So combine, we then, for this top part, we distribute that 2 out, and then we simplify, right? So I'm left with 2x plus 2 over x squared, all right? So again, in summary, we look at our original problem, multiply the first rational expression by the reciprocal of the second, and then we end up simplifying using the processes that we know. Okay, so then for a couple more examples here, if we need it, take the second one, flip it, and then multiply and simplify. All right, multiply and simplify. So again, hopefully this is nothing too terribly difficult for you or anyone. Okay, it's using the processes we already know, to solve different or unique looking problems. Okay. Ooh, sorry, I saw in my eye. All right, so again, something a little bit potentially more complicated here is we have a binomial on top of both of these. So we're still going to follow the same processes though. All right, so we convert it by flipping that second, right, looking at the reciprocal, and then we're going to multiply both of these together. So we then multiply it out. The top, we're going to distribute that x to the 5th. The bottom, we're going to FOIL. All right, so then when we simplify our product, it looks like this. All right. So then when we're looking at this, right, we talked about these things called acceptable values, right, or things that are unacceptable or excluded, more likely, right? And those are things that are going to make our x value or end up with a 0 in the denominator. Okay, it's going to end up with a 0 in the denominator. So if we're looking at this problem here, all right, if we're looking, especially looking at the original problem here, if I have a -1, sorry, positive, I meant positive 1, sorry. If I have a positive 1, right, 1 minus 1 gives us 0. Sorry, if I have a positive 1, that's going to be an excluded value of x, right? Because if I plug in a 1 here into this problem, or a 1 down here into this problem, that's going to not give us a value on bottom, right? It's going to give us a 0, which means it's undetermined, right? So if we were to go through, we could look at excluded values of x, right? And for this bottom one here, okay, x to the 5th, well, 0 to the 5th power would give us a 0 here, right? So those are going to be two values that make this undefined. So those would be our two excluded values of x. Those would be our two excluded values of x. All right, so tying it all together here. All right, we've talked about simplifying our answer. We've talked about simplifying if possible. So let's look at one where we actually can do it. All right, so first off here, again, remember, converts. We have to flip that second value. Then we multiply, right? We multiply our original by our reciprocal. Okay, so we're going to distribute on top and we're going to FOIL on bottom. All right, but before we do that, since we have something that is a perfect square on top, right? We have a perfect square on top. We know that we can factor this out further than this x squared minus 4. We know we can factor this out more than just x squared minus 4, right? So by that, I mean it can come to this x plus 2 multiplied by x minus 2, right? And your first thought might be, well, why would we do that? Well, if you look here, I've got an x plus 2 in my denominator. When I end up factoring out this x squared minus 4, right, factoring out this x squared minus 4 into my two binomials, I can actually cancel out an x plus 2 on top and an x plus 2 on bottom, right? So I can actually cancel those out. So since I'm able to cancel those out, the only thing I have to distribute on top is my x cubed to my x minus 2, right? So when I simplify, I'm left with this new expression here, this much, much smaller expression than if I would have left, this as x squared minus 4, okay? And then again, remember, they included the values that are not acceptable for x, or the two values that are going to make this expression 0. Okay, they're looking at what two values will make this expression 0. All right, and what I want you to notice here is that when you should look for excluded values of x is after you combine it and before you start simplifying. Okay, so if you look right here, and all right, if you look right here, it is in the simplest form for you to figure out what values are unacceptable. All right, we don't go all the way back up to the original, because if we did that, it would look like the values would just be -1 and 0. All right, we have to look here at our combined form when we actually combine them together. So then we look at these two values that would give us 0. So we would have our x -1 and x can't equal -2. All right, so when we're looking at our excluded values of x, you look at the combined version before you start multiplying out and simplifying. All right. So looking at this guy here. All right, looking at this guy here. Runners and their rational expressions. So if we take a look to actually digest it to what this is saying, it says 2 marathon runners are training for the London Marathon. One lives in the United States, other lives in the United Kingdom. They both train every day and they compare their running data. All right, however, you're going to notice here that the distances are in different units. So for here, you've got the distance in miles for the US runner, and in the UK, you've got the distance in this thing km, kilometers. All right. So for the first question here, without doing any calculation, which runner do you think would run the fastest or is the fastest? All right. And if you look at any of these values here, it looks like potentially, right, unless you know the conversion factor, it looks like this UK runner might be faster. So if I said UK, right, yeah, it might look like the UK runner is faster, because at 16 and 16, they're running it much quicker. But it's hard to tell without actually converting the distances. All right, so then looking here, it says in order to compare the distances and times for each runner, the units will need to be converted to either miles or kilometers. All right, whatever number you work with, it doesn't matter, right, as long as they're both in the same number. All right. And then they gave you an example here. So 2 miles per hour, that's what MPH stands for, miles per hour. So how we write that, and this is going to be very, very helpful for those in your science classes, right, when you're talking about conversions here. All right. But when you have something that says something per something, that means you divide. So here we've got miles per hour. So I've got miles over hours. So I run 2 miles per hour, right, or per 1 hour. All right, so that's how you would look at that. So if I look here, the unit conversion for miles to kilometer is 1 mile equals 1.609 whatever km. All right, so to write that as a rational expression, it's either of the first two options. Okay, because this is saying 1 mile per this many kilometers and this many kilometers per 1 mile. All right, so both of those options are correct, right? Just depends on if you're going from miles to km or km to miles. All right, so then when we look at this expression here, okay, we look at this expression here. If I just took my my XKM and I multiplied this out, it would look like X over 1.6 equals Y, right? X over 1.6 equals Y. And again, we know that this is going to be true because I have a KM on top and a KM on bottom. So these KMs would cancel and I'd only be left with something in miles. All right. Ooh. Okay, so then when I look here at actually comparing, if I look here at actually comparing, all right, you would have to go through and do the conversion. So I'll just type in conversion. All right, but doing this, we're going to know that the US runner ran more. Okay, the US runner ran more. And the reason we know that is because if we were to do our conversion, 14 miles is greater than 14 kilometers. All right, because 1 mile equals 1.6 kilometers. All right, so 1 mile is more than a kilometer. Okay, so 14 kilometers, if we were to convert that, would equal 8.7 miles. So the US runner is much, much faster. All right, so then when we do this and we run and we convert, it says calculate and compare seconds per mile. All right, seconds per mile. So we would have to convert kilometers to miles. We'd have to convert these times, which are shown as hours, minutes, seconds. We'd have to convert all of these into seconds, or just the one that's highlighted. And if we were to do that, we figure out that the UK runner is faster if we're looking per mile, right? He's faster per mile, but just barely. All right. And again, how do you do that? Just taking a second to digest this. So you've got 2 hours, 36 minutes, and 45 seconds. All right, so they combined it into all one big step. I don't care how you do it if you want to do that in multiple steps. But basically, you should know that there are, in 2 hours, right? So there's 60 minutes per 1 hour, right? This is where that notation is going to come in handy. 60 minutes per hour. All right, so you write 60 minutes over 1 hour. That cancels hour with hour. All right, you're left with then 60 minutes. Well, I need this in seconds, so I'm going to do another conversion here. 60 seconds per 1 minute. So I can cancel minutes, and I am left with, from this 2 hours, I'll be left with whatever 2 times 60 times 60 is. That'll give me how many seconds I have from my 2 hours. All right, then for my 36 minutes here, 36 times by 60 over 1, that would give me however many seconds from my 36 minutes, and then I add it all together with my additional 45 seconds. So I'm left again with 9,405 seconds for this US runner here. All right, so then if we skip down here for the US runner, right, if we're looking for seconds per mile, which means I put seconds on top and I put miles on bottom. So for my US runner, I have my 9,400 seconds that I just calculated over the 14 miles that they just ran. So that's how I got my 671 seconds per mile here. All right. But my UK runner, there's one more step, right? They're still the same conversion of their time, but now we have to convert from kilometers to miles. All right, so how you show that is you have it written, you've got your 14 kilometers, and we know that for every 1 mile, there's 1.6, it was like 0.9 something, okay? There's 1.6 kilometers per every mile. So I cancel out kilometers on top and on bottom. I'm left with this 8.7. So then again, I take their time, which we just calculated, divide by their new mileage, and then I get my seconds per mile. Okay. Again, you have this at your disposal, so take a second to digest it if needed. All right. But in general, when we're dividing by a rational expression, it's the same as multiplying by, the reciprocal. right? We flip the value and we multiply by the reciprocal. All right. So again, here we would flip this guy and multiply by the reciprocal. So if I flip this top one, I've got 7 times by x and 7 times by 5. So it's going to be 7x plus 35 on top. And then if I were to do the same thing on bottom, my 3x times by x squared minus, or sorry, my 3x times by x minus 2, that's going to give me 3x squared minus 6x. All right, same thing, flip the top. All right, flip the top. Or sorry, flip the second one, right, and multiply. So I've got 4x times by x, so that's going to give me my 4x squared, my 4x squared, and then I have my 2x plus 1 multiplied by my x minus 3. And again, this is where these are very, very similar. Okay, they're very, very similar, and you're going to have to make sure that you're writing these down so you don't mess it up with losing a value or two. Okay, so again, make sure that you're writing these all out, because off the top of your head, you might get a little bit confused. All right, so I'll let you try this one and then the one on the next one there. All right, so again, looking at this, we flip and we multiply. So 1/2 multiplied by 3/2. So that turns into 3/4. So 3/4. All right. Then if we look here, okay, again, we flip this and we multiply. So I end up with 2 multiplied by x plus 1. So that gives me 2x plus 1. And then I've got my 3x. So my value is going to be d there. All right, and if this was simplified further, obviously we would do that. And then this one, again, I'll let you try on your own. It seems complicated at first, but things end up combining, right? The way that we know, you just have to flip and multiply. All right, same process here, flip and multiply. All right, so if we look at our study guide here, we look at our study guide. All right, you're going to find out, again, fractions do the same thing as rational expressions. All right, so we're going to, when we're just looking at multiplying, okay, we're going to multiply the numerators, multiply the denominators, simplify the product, and list any variables that make the expression undefined. So again, when we multiply out, we've got x and x plus 1. So if x is equal to 0, this is going to be undefined, and if x is equal to -1, it's going to be undefined. All right. Then same thing with dividing fractions, except we have one step. So first we switch the numerator and the denominator, or we change the divisor to its reciprocal, right? So doing that flip. And then we multiply the dividend by that reciprocal. So we multiply our original by that reciprocal, and then we simplify the product. All right, we'll do the same thing with our rational expressions here. So we change it to the reciprocal, we multiply, we simplify if necessary, and then we list any values that would give us an undefined denominator. All right, and again, we only have this undefined denominator once we have flipped and multiplied. All right, so again, we're looking at once we have flipped and multiplied. So I'm looking at this stage here. All right, so looking there and not all the way back at the original. Okay, so if you look at your practice problems here in your checkup, okay, if you look at the practice problems in the checkup here, it is, all it's asking you to do is do basic multiplication ones and division ones. So again, I would really, really suggest that you go through and do these. But again, you're following the same process every single time. All right. The key here is just going to be making sure that you do them, and then you check your answers against the answer key. All right. For this one here, we have 2 quizzes. So multiplying the rational expressions and dividing the rational expressions. So yes, you will have to do both of these quizzes here. All right. But it is specifically telling you that this one's all about multiplying rational expressions. So go through, if you're confused, rebone up on that one, and then take that quiz. Same thing here. Refamiliarize yourself here with dividing, and then take that quiz. So you'll have 2 quizzes for 1.4. If we go right into 1.5 here, okay, so now we're looking at adding and subtracting rational expressions. All right, So adding and subtracting rational expressions. And just like we did with multiplication and division, it's going to have a similar process to what you would do with normal fractions. All right. So for this one here, it's really easy to add and subtract rational expressions if they have the same denominator, right? If the bottom's the same, then you just leave it and you add or subtract the top as you would normally. So if these are both 7s, we have 2 plus 4, that gives us 6. If these are both 5s, I've got 1 minus 2, which gives me -1. All right. So if the bottoms are the same or the denominators are the same, it's an easy problem here. All right. So sure, we'll add them together, subtract, right? And the same thing goes for rational expressions. If it's the same on the top and the bottom, all you have to do is treat it like a fraction. So for this one here, we would add it. So we'd have x plus 4 on top and our same x minus 5 on bottom. All right. If we had, again, same top, same bottom, but we're going to subtract now, I can simplify. So I've got x minus 4 minus x, right? So I simplify that down. So that gives me 2x minus 4. 2x minus 4. All right, you might be thinking, where did that 2x come from? Right, you have to distribute this negative sign. Right, you have to distribute that negative sign. So this is like saying x minus 4 plus x. So that's how I get my 2x minus 4 on top there. So again, being really, really careful with your distribution and making sure you keep track of all your signs there. All right, so again, as you've seen, if the bottom or the denominator is the same, then you can easily add them together, all right, or subtract them together. So a couple examples, again, you can look through these on your own, but just being really, really careful with, especially with the negative signs, right, making sure that you're distributing that negative sign to both of your values, okay? Now, if they have different denominators, we have to find this thing called a common denominator. Okay, a common denominator. And there are multiple ways of finding a common denominator, but the first way we're going to look at is if you just multiply the two denominators together. Okay, so what that means is if I've got 1/6 and 7/10, well, the two denominators are 6 and 10. So to find the common denominator, we're going to multiply each of the fractions by the different denominator. All right, and pay special attention. You can't just multiply the bottom by 10 and call it a day. You have to multiply the entire fraction by something like 10 over 10. Okay, so this one you multiply 10 over 10. This one you'd multiply 6 over 6. So when we're left, our fractions turn to 1 over 6 plus 7 over 10 turns to 10/60ths and 42/60ths. All right. But now since we have a common denominator, we can just add the top as we would, and then we can simplify down further. So the smallest common denominator, right? If we use that to get down 52 and 60, we can get that down to 13 over 15. All right. So again, the steps there are going to be to multiply, right? Multiply our original fractions by the common denominator, right? Get it to the common denominator, simplify, and then reduce if possible. All right. So the same thing here is going to work with rational expressions. All right, it's going to work with rational expressions, but it might not be as obvious, or it might be a little bit more labor intensive here. All right, so to find the common denominator with these guys, right, we're going to multiply. Again, I know it looks pretty nasty, but we can do it. All right, so you're going to multiply each of the sides of the fraction by the denominator of the other, right? We're going to try to multiply by that expression so that we can get that common denominator here. All right, so if I've got x squared plus x, I'm going to multiply it by the denominator of my second one. So when I distribute that all out, right, I can do that, and that's what I'll get. Same thing here. We had to multiply the top and the bottom by this x squared plus x. All right, so then I can get this guy, and then knowing the process here, we would be able to combine like terms here and simplify. All right, so again, if you want to see what the answer is, you would type it in here. But if I simplify the top, I've got 8x squared plus 5x minus 3. So 7x squared plus an x squared there. I've got my negative 2x plus 7x, which gives me my 5x, and then my negative 3 remains unchanged. Okay, so another way that we can find it, the common denominator, is if we do this thing called least common multiple. Okay, least common multiple. And what that means is if I break apart both my denominators into the factors that make it up, right? In order to get 6, the least common factors, right? The smallest common factors that make up 6 would be 2 and 3. 2 and 3. And the ones that make up 10 would be 2 and 5. All right? So if I look at this, they both have 2, but then I can also multiply by 3 and 5. So my least common multiple here would be 30, right? I take the number that they have in common, and then I multiply by whatever's remaining. So here, my least common multiple for these two would be 30. So to make it a little bit easier here, I only have to multiply by whatever is missing from this least common multiple. So here, since this is already 2 times 3, it's just missing the times by 5. So I multiply by 5 over 5. This one is 2 times 5. It's missing that 3, so I multiply by 3 over 3. All right? And when I multiply those out, this is what I'm left with, 5/30 over 21 over 30. Again, if I simplify, it's still the same thing as we see up here. We're just showing it in different forms. All right? So now they have the common denominator. I can add them together, and I can simplify down from there if possible. All right? I can simplify down from there if possible. All right? So you can do the same thing with this least common multiple as the common denominator, right? So you can do this with rational expressions. But for rational expressions, it may take 1 or 2 extra steps here. So the first one would be you have to factor the denominator of each rational expression, okay? So you have to factor just like we did with the numbers. So here, x squared plus x, we can factor out an x, and then I'm going to have an x plus 1. Here, right, we can use everything we learned in semester 1, and we're going to get an x minus 3 and an x plus 1, right? So here, this bottom equals x times x plus 1. This bottom here equals x minus 3, x plus 1. So if we notice here, we have an x plus 1 in common. We have an x plus 1 in common, right? So I keep my x plus 1 for both, and then for my least common multiplier, I have whatever is remaining on both sides, right? So my least common multiplier is that combination of all of the factors, right? So I've got my x plus 1 from both, and then I've got my x minus 3 and my x over here. All right, so that's my least common multiple. All right, so now when I'm looking for my common denominator, I just multiply by whatever is missing. All right, I multiply by whatever is missing. So again, over here we are missing that x minus 3, so I'm going to multiply my top and my bottom by x minus 3 over x minus 3. Over here, I'm only missing an x, so I'm going to multiply by x over x. And then I would get obviously my least common, I get my common denominator. I get my common denominator, and then I could just add those together using the same process that we have. Okay. Now, again, subtracting is not much more difficult. It just requires a little bit more attention. Okay, you got to remember that this negative sign gets distributed throughout. So if we look at this here, my least common multiple, all right, I've got I've got my my factors here for my x squared, which is x and x, and my factors over here for my x squared minus 2x, which gives us x times by x minus 2. All right, so my least common multiple would be an x squared and x minus 2. Would be x squared and x minus 2. And the reason this is x squared, okay, the reason this is x squared, in case this isn't obvious, all right, so this is like saying x, oh, sorry, this pen is always awful, x times by x, okay? So remember, if we had something in common, like an x here and an x here, we only showed it once in the least common multiple, all right? So that blue x comes from those two coming together, all right? Then I have my x minus 2, which is fine, right? We know that, we pull, but I have a leftover x here. So this is where we get that second x from, okay? This is where we get that second x from. It's a leftover factor from our x squared, okay? We have a leftover factor from our x squared there. All right, so now that we found our least common multiple, we can multiply by what we need to in order to get our common denominators in both of those expressions. All right, once we multiply them together, we're going to subtract. All right, but again, being super, super careful that you take this negative sign and you have to distribute it across the top to all those values. Okay, you have to distribute across the top to all those values. All right. Sorry. So first, it's good to see if you can, it's saying first, if you can simplify an answer, go and do it, right? If you can simplify it, go and do it. And by that, or how would you know you might need to simplify, okay? You look at the top, look at the numerator, okay? It's a very complex numerator, and it looks like maybe we might be able, since there's a factor down here, if we can find our two factors that make up our numerator, maybe we can cancel out this x minus 2. All right, but if we look here, we actually factor and we can't cancel it out. All right, so it turns out there's no common factors between our numerator and our denominator, so we can't actually cancel anything out. All right, but it is always a good thing to check, because if you can simplify it to start off with, right, then when you have to add in other rational expressions, it becomes a lot easier. All right, but regardless, when if we were able to simplify, we would still have to remember that x can't equal 0 and x can't equal 2. So even if we were able to cancel out for this one, we'd have to go back to our original expression here and remember that x can't equal 0 or x can't equal 2. All right. So then if we look here at a real world situation, we've got this car wash problem. All right. So apparently it takes you 45 minutes to wash a car alone, and it takes your friend 30 minutes to wash a car alone. All right, so if you guys work together, how long will it take you to wash cars, right? And to solve this problem, we have to understand that rate is equal to work over time, okay? So basically the rate at which you wash a car is how much work do you get done per the amount of time. So for example here, I wash one car in 45 minutes and you wash one car in 30 minutes. All right. So if I add them together, this is the rate of us working together, right? It says are both, which means the rate of us working together. All right. So how long is it going to take us to wash a car? All right. Well, first off, we would have to find a common denominator here, right? And there's a lot of different ways you could have found a common denominator, right? We just talked through a bunch. But if we found a common denominator as 90, we could figure out, hey, if we add them together, we're going to get 5/90ths, which simplifies to 1/18. All right, 1/18. And if we remember, this was work over time, or how many cars could I wash in a certain amount of time, or how long did it take me to wash one car, right? So if our answer here was 1/18, this means I can wash one car in 18 minutes. So the question asked us, how long will it take you to wash one car? Our answer is 18 minutes, not 1/18. Again, this is another example of you have to be really, really careful and particular with writing your answers. Yes, mathematically we ended up calculating 1/18, but what this means in actual solving the problem terms, it means 18 minutes. Okay? Means 18 minutes. And what they said here was it might not be obvious as to how we got this answer, but if you think about it, okay, 90 minutes, right, is an hour and a half. So in an hour and a half, I can wash 2 cars and you can wash 3 cars. So together we can wash 5 cars in an hour and a half, or at a rate of 1 1/3 cars per hour. I'm sorry, 3 1/3 cars per hour, okay, or 18 minutes. All right, so both of those ways of thinking are correct. Whatever one works for you, by all means, continue with that. All right. But this is just a real world example. Okay. So then here, if we look at another real world example, we're looking at a tile installer. Okay. So he has a set formula for how to calculate what's called bids, right? So when you are looking for someone to do something on your house, they can give you this thing called a bid, which is an estimated cost. So you know kind of before going into it about how much they're going to charge you. All right. But a lot of bids are based on hourly rates, right? So labor rate. Okay, they're based on labor rates. Sometimes they're based on how long it takes them to do something, right? So per hour. Okay, so for this one here, he charges a labor rate of $2.75 per square foot, and he adds a 15% charge onto material cost. In addition, he pays another installer, so a helper, at a rate of $12 per hour. He installs at a fairly consistent rate of 20 square feet an hour, and his helper is 15 square feet an hour. All right, so those are all the facts that we need here. Now it says, which expression represents the amount the installer charges for labor? Well, we know right here the installer has a labor rate of $2.75 per square feet. So it's going to be 275x, right? He charges that for every square foot. All right. Which expression below represents the material upcharge? Well, he adds a 15% charge onto material costs, right? So 0.15 times by M. Right, so that's the next step. Which expression below represents the cost of the helper of the helper for the tile installation? All right, so now this is where don't get confused. Okay, so he has a rate of $12 per hour. $12 per hour. All right, and if hours are X, it's $12 an hour. Okay, but we can install 20 square feet an hour from the original guy and 15 square feet an hour from our helper. So adding those together, that's 35 square feet in an hour. So what we can do is our rate now becomes $12 an hour, okay, from the tile installer. That's his rate. But we're going to take our time, X, and we're going to divide it by 35. Because X is how many tiles we're going to install, right? And if we install 35 together an hour, okay, that's going to tell us how many hours we're going to work. There you go. All right, this is accurate, but it can be simplified further. Yes, correct. Right, so don't make a mistake like me. All right, so 12x over 35. Okay, so always pick the simplest form if there is one. All right, so looking at this, our labor charge, again, it's $2.75 per square foot. All right, per square foot. this material here is 0.15 times by whatever the material costs. And then the cost of the helper is 12 times by the number of square feet divided by 35, because together they can install 35 square feet an hour. All right, so it says, which is an example, estimates the profit for each job. So the profit for each job would be, well, obviously, whatever labor charge, okay, plus the material charge, but we have to subtract the cost of our helper here. So we're going to have an addition and then a subtraction. Again, keep doing that. Okay, it's simplified. In its simplified form here, we have 84.25x over 35. All right, and that's a good catch there. So if I can simplify this, I do. And the mistake that I made is that I didn't remember that this 2.75x, since it's got an x here and an x here, there's like terms. So since there's like terms, we can combine. All right, but in order to do that, you would have to convert this 2.75, you'd have to find a common denominator. So I'd have to multiply at this top and the bottom by 35. Okay, because this is like saying 2.75x over 1. Okay, because anything divided by 1 is itself. So again, in order to get this so that I can simplify, right, I'd have to have 35 over 35 and multiply it here by my original. Okay, so then here, always a good problem if we know that it's going to be 295 square feet, all right, and we know that the tile comes in boxes of 20. They're all 1 square foot tiles, all right. How many boxes are we going to take? It says round your answer to the nearest whole number, because again, we're not going to take half of a box or 3/4 of a box. So if I just took 295 divided by 20, because that's how many come in each box, all right, my answer is going to be 14.75, but again, it says round to the nearest whole number because I'm not going to get 3/4 of a box. So my answer there would be 15. I need 15 boxes to finish the job here. All right, so then if I know that I need 15 boxes, okay, you can calculate your total profit. And what I'm going to do is I'm going to type in profit. Okay, the response is 872.11. But how did we get that? All right, well, we know that we have $72 per box of tile. We know we're going to buy 15 boxes of tile. So that becomes our value for M, right? That's our material cost. So at our 0.15 M, we plug that new value in, all right? We know we need to lay 295 tiles, so that's our X value there. That's our X value, so we plug in 295 for X. Then once we plug in, we can simplify, and then we are left with our profit here. Okay, we are left with our profit. All right. So if it asks the question, what would the installer charge the homeowner? Okay, what would they charge the homeowner, right? We would, we would add on everything. Okay, we would add on just the 2 costs that we had. All right, so we would have the cost of the homeowner would be the cost of what we said, our labor per square foot, so our $275 per square foot. We would add on the cost of the materials, right? We'd add on the cost of the materials, and then we would also add on our upcharge of 15% to the material charge, okay? We would add on our upcharge, okay? And we don't add on the cost of the laborer or subtract the cost of the laborer because that's what we're doing ourselves. So what we're going to do is we would charge the homeowner $2,053.25. So that would be the cost of the homeowner. But after I pay for the materials, after I pay my helper, I'm only left with $872. Okay? So that's again another real world example there. All right, so to add or subtract a rational expression, they both need to have a common denominator. All right, they need to have a common denominator. All right, and there was two ways we found of doing that. We had multiplying out or finding the least common multiple. All right, we had multiple ways of doing that, either multiplying both together or finding the least common multiple. All right, for the sake of time here, I'm going to skip these guys and let you go through it. But remember, if they have the same denominator, it's easy. You just add or subtract, being careful to your signs. All right, if it's not the same, that's when you have to find that least common multiple, or at least the common denominator there. All right, so again, this one, not a common denominator. You've got 1/2 and 1/3. So if I have this, if I multiply this by 3/3, I can get 3/6. Over here, I can get 2/6. So 3/6 and 2/6 gives me 5/6. All right, and once I get 5/6, I can't simplify down any further, so I'm left where I am. All right, this one, they have the same denominator, so x plus 3x, that gives me 4x over 2. 4x over 2. All right, and 4x over 2 is not an option. 4x over 2 is not an option. So if I have 4x over 2, though, 4 and 2, I can divide both of those by 2, so I'm left with my final answer of 2x here. All right, I'm left with 2x. Okay, so then 3 and 4, I'm going to leave for you to try. Again, they might look a little bit uncomfortable at first, but again, you follow the same process and you're going to find the answers simplify pretty nicely here. Okay, so looking at our study guide. Okay, looking at our study guide here. All right, I have our rational expressions. Again, if they have the same denominator, you either just add or subtract them as the way they are. Okay, so if they have a common denominator, you add the numerators, keep the common denominator, simplify, and then list any values that x can't be. Right, you list any values that x can't be. Okay, to add or subtract fractions that have different denominators, you have to find a common denominator. So we had two different methods. We either multiply the two denominators together, or we find the least common multiple. All right, those were our two methods. So when we do that, though, we find the common denominator, we rewrite the fraction with the common denominator, we add or subtract, right, whatever it's asking us to do, and then we simplify. And then if we can reduce our fraction any further, we do that as well. All right, so again, with these rational expressions, find the common denominator. Multiple ways of doing that. Whatever your preference is, by all means, go ahead and do that. All right, then you write the fraction with the common denominator. You add or subtract, again, being really, really careful that when you have a subtraction, you have to distribute that -1 sign throughout. And then you simplify and list any values that x can't be. All right, you list any values that x can't be. And again, remember, this is the values that x can't be once you found the common denominator. Once you found the common denominator. So I'm looking right here. My common denominator is x times by the quantity x plus 1 times by the quantity x minus 3. So I have three numbers, or three values that x cannot be, otherwise my denominator is going to equal 0. All right, so looking again here at my checkup, it's just asking you to find the sum or the difference, okay? So all of these are going to start off with the question of, okay, well, first, do they have a common denominator? All right, if they don't have a common denominator, you have to find it. There's two different ways we found them. All right, once they have a common denominator, then you can simplify the way that we've been doing, okay? So hopefully not too terribly difficult here. All right. There is one quiz in this unit, so there's only one quiz, and it's on both adding and subtracting. So again, same thing, you're looking for common denominators. If no common denominators, then you have to find a common denominator. All right, and again, being really, really careful with, if there's a way to simplify, do it. If there is a way to simplify, do it. All right. Then here, our final unit we're going to talk about today, 1.6. So this thing called inverse variation. All right, I want to point out here, there is a quiz and a practice. Remember, this practice, if you want to do it, is extra credit. Okay, this practice is extra credit. It's not mandatory. Only the quiz is mandatory. All right. So looking here quickly at inverse variation. So we talked a lot yesterday about this thing called ratios and how they're proportional to each other. All right, and what that means is if I looked at the ratio of width to height, it was 3/4, and it was consistent between these two pictures, which means they are proportional to each other. There's no distortions. They're the same general shape, right? They're the same ratios to each other. They're just a smaller function. All right, and if I rewrote this, okay, I could write this as width is actually 3/4 times by the height, right? I just move height to the other side by multiplying both sides by height. All right, so again, if I were to, I know it's a little bit confusing here. We have width over height is 3/4. When we go to this next slide here, they write it as height over width. Okay, they wrote it as height over width, which is 4/3. Okay, which is 4/3. But they simplified it down here to 1.3 for you. All right, so our width here is, our height to width ratio is 1.3. All right, so what that means is the height will change, the width and the height will change to keep this ratio the same at 1.3. So if I made the width larger, right? If I made the width larger, the height changes as well. So the width larger, height gets larger as well. Same thing if I go in the smaller direction, right? It's trying to keep that 1.3 ratio. All right. So it's like saying if I have my width, I'm going to multiply by 1.3, and that's how I'm going to get my height, right? That's how I'm going to get my height. So you can write this. And when we write it like this proportion that we had of height to width, we can now write this as a linear equation. All right, this should look familiar here. If I were to just simplify this into variables as h and w, this would be like saying h is equal to 1.3w, or y is equal to 1.3x, right? It becomes a linear equation, right? So the graph of this relationship, if it's a linear relationship, it should look like a linear line, which it does, right? It should look like a linear line. And this is called a direct variation, right? And why it's called direct is because if I increase one, it's going to increase the other, right? At a constant multiple, right? Or at a constant factor. So our factor here was 1.3, right? So if you look here, my width is 10. If I took 10 and multiplied by 1.3, I get my 13 value here. All right, so if I go back for a second, again, remember, our height is equal to 1.3 times by our width. So if I look at my width here, my width is at 10. 10 times 1.3 gives me my 13. All right, and again, if I move this value, doesn't matter what the absolute value is going to be, it's going to try to keep that 1.3 constant ratio, right? So if I go all the way up here, 20, okay, 20 times 1.3 gives me 26, which is why my height is at 26. All right, so again, this is called a direct variation. It is a direct variation, and it results in a graph that looks like a linear line. All right. So you've seen that the ratio between height and width, right? Since it's got this constant, it's called a direct variation. Direct variation. But if I have height times width and that equals a constant, right? This is a new shift. Okay, so this would be like saying height times width equals a constant. All right, if I multiply them together, that is a constant. So that's a different type of variation. And that is called an inverse. Okay, it's called an inverse variation. But to show you where this might be handy, is if you have a painter. So Scott is a painter. He only has enough paint to cover 100 square meters of a wall. All right. So he can only cover 100 square meters of a wall. So what areas or what rectangles could he cover before running out of paint? So he could do maybe a 10 by 10 here. He could do 100 by 1 or a 1 by 100, right? Whatever it is, it can only equal a total of 100, right? He only has 100 square feet that he can cover. So this would be called an inverse relationship, all right? And what we could do is we could solve for height, right? So if we solve this equation for height, we would divide both sides by width, right? We could divide both sides by width. And you've got height equals 100 over width, or y equals 100 over x, right? 100 over x or 1 over x, right? It looks like our parent function for an inverse relationship, right? It looks kind of like our parent function that we had of f of x is equal to 1 over x, right? Now notice, again, it's a rational equation because it has two variables in fractional form. Now, it's called an inverse relation, inverse variation, because it has an inverse relationship, okay? It changes inversely. Again, if one goes up, one goes down. That's what it means by inverse. So as width gets really, really large, height gets really, really small, okay? Oppositely, if width gets really, really small, height gets really large, okay? And hopefully you're noticing here, it's making a shape of a graph that's similar to what we've seen for our inverse functions. Okay. So then looking here at inputs and outputs, okay, inputs, those are the things that we're inputting, right? So our independent variables, our x values. Our outputs are our dependent variables or our y values, okay? So we can see the difference in our direct and our inverse relationship based on our inputs and our outputs. So for here, for our direct variation, if I have my input, right, I multiply it by a constant, that's how I get my output here. So I multiply it by this constant value, all right? For this guy, I have my constant, and I'm gonna divide it by my input. All right, so again, as this one gets really large, my output gets really small. So I have this inverse relationship here. So I want you to take a closer look here at the direct variation. And again, I'll just point out a couple examples. Again, the 10 and the 13. It's also showing you if you go to the output of 2 and the answer is 2.6. Okay, so again, we could plug it into our relationship. 2, if I go to 2, that should be 2.6. All right, so again, plugging that in, 2 times by 1.3 gives me 2.6. What it's also saying is that since this is a relationship, if I were to double this, so go to 4, it should be at whatever double of 2.6 is. So if I go to 4, that should be at 5.2. And it is, because 2.6 times 2 is 5.2. Same thing earlier. Like I said, we were at 10 and 13. If I double 10 and double 13, that should get me to 20 and 26, right? It's going to be a constant proportion throughout. However, when I look at my inverse variation, right, one goes up and one goes down. Okay, but they're going to do that at a constant ratio. So for example, if I start at 10, 10 here, if I bring my width out to 20, right? If I bring my width out to 20, here we go. Look, I doubled my width. I doubled my width. So I should have my height, okay? Because remember, it's constant divided by width. So if I make this 2, it's like saying, okay, great, height, you're going to be equal to 1/2 of whatever you just were. Same thing, if I take my width and now make it half of what it was, so we went from 10 to 5, I made it half of what it was. It's like multiplying by 2 for the height. All right, again, it's going to form that shape there. Okay, so how could we find the constant? How can we find our constant? Easy, you just substitute in any two numbers. Okay, so if we know that we have a direct relationship, that means our output equals constant times by input, or y equals constant times by x. Okay, y equals constant times by x. So I pick an x and a y value. So I have 8 and 10.4. So I plug in my input and my output, or my x and my y, and then I solve for my constant. I can do the same thing for my inverse, right? I can do my same thing for my inverse. It just might look a little bit different. Here, this one is divided. Here, this one is multiplied. But regardless, I'm able to solve for my constant value in both of them. All right. So two special proportional relationships are called direct and inverse. Okay, direct and inverse. All right, direct variation is where you have that linear increasing line. Inverse is where you have an inverse relationship of one goes up and one goes down. All right, so looking at this, the graph on the left, okay, it is obviously an inverse relationship. Okay, it's got an inverse graph here, but then also look at the proportions, right? So if this is 1, if I go to 2, this is doubling, that should half. Right here, this goes from 2 to 4, so that's doubling again, but my height should half. So since it follows that pattern, that makes it an inverse relationship. All right, immediately off the bat, this linear line tells me it's a direct variation. And if I want to check though, just to make sure, I can. All right, but that linear line there is telling me it's a direct variation. Now again, to solve for the constant in this equation, you just plug in two values, right? So I've got 2, 5 as my width, 2, 5 as my width and my height, right? That's a point on my line. So I plug in 2 for my width, I plug in 5 for my height, I end up with a constant of 2.5. All right, and I'll let you try this one on your own here. But again, you just pick any of these points, plug it in for the height and plug it in for the width. Again, being really careful that width here is your x value and height here is your y value. All right, being very, very careful. So right here, it says, is the relationship inverse? That's what it's asking you. So when you pull it, you can see, okay, no, it's keeping the same shape. It's keeping the same shape. It's just changing how large. Oh, sorry, that should have been false. It's keeping the same shape. So it is not an inverse variation, right? Since it's keeping the same shape, this makes it a direct variation. Okay? If it was changing its shape to keep the total area the same, that would make it an inverse. All right? For here, find the constant value with the equation below. All right? Well, again, looking, it's an inverse relationship, and then you pick any point, okay? Pick any point. It started at 10, 5. So height equals constant times my width. I plug in 10 for my width, plug in 5 for my height. So I'm going to figure out that my constant is 0.5. All right. For this one here, if you can't tell originally by looking at the equation, this is going to be an inverse relationship. If you need to draw your graph, right, draw the graph and notice that it's an inverse relationship, okay? So I'm going to plug in 10 for my width, I'm going to plug in 11 for my height, and when I solve for my constant, it's going to give me 110. All right, same thing down here. You've got 7.5 and 10. So you've got 7.5 as your height and 10 as your width. You're going to solve for your constant. That's going to give you 75. All right. So then here, this is talking about experimenting with a lever, and I'll go through this really quickly, but basically this is like looking at a scale. Okay, so right now this is saying that this side weighs more, right? And if we look at it, it's kind of obvious here. Well, this one has more weight. But if we move where things are located, right? So even though this one has more weight, since this one is closer to the center of the lever, okay, closer to the center of the lever, it now becomes perceivingly heavier since this is farther away. All right, and there's a point here where we can get these two to be about even, if not exactly. There you go. Right, there's a point here where these two weights will equal each other even though they're not the exact same weight. Right, this one's 100 centimeters away and this one's 90 centimeters away. Even though this one has more weight, okay, because of the difference in distance, they're going to look the same and have the same pull on either side of this lever here. Ooh, too many skips. All right, so balancing the lever, right? So I just balanced that lever for you. You can make any combination and play with figuring out which one weighs more and which one weighs less. And again, at some point, they're going to be about even, if not exactly even. All right, and so this one here, it keeps flipping back and forth. So again, that's probably an error in the programming here, that it's not that specific. So I can keep throwing weights on it, right? And you can play around with trying to get these two to balance. But basically, there is some combination of weight and distance that's going to equal the different sides here. So this one's saying, can we just move the right-hand side to make it equal? And the answer is actually yes, right? So look, even though this one has 900 and this one only has 610, okay, we can make them equal to each other if you play with the different distances on the levels, okay? You can play with the different distances on the levels. All right, and this is an example of an inverse relationship or inverse variation, okay? Okay, because as we increase the distance, the weight goes down. As we increase the distance, the weight goes down. All right, so this is an example of an inverse variation, talking about input and output of a desired mass, okay? So our input might be distance and our output would be mass. And our constants here would be whatever weight is on top, right? So 900 would be our constant for this one and 610 would be our constant for this one. So we can play with that relationship there. All right, quickly glossing through because I know we're almost done with class here. Okay, we have our direct and our inverse variation. So again, looking at either the ratio being constant or the product being constant. Okay, so by that it means if you look at, I've got output equals constant times by input, or output equals constant divided by input. All right. In a direct relationship, as one increases, they both as one increases, they both increase. Okay, or decreases. In inverse relationship, as one decreases, the other increases. All right, and then if it looks here, if you double the input for a direct, you would double the input for the output. If you double the input on an inverse, you're going to have the output. Right, so again, knowing those tricks there. And for a direct relationship, the size changes, but the shape does not. For an inverse, the shape changes, but the size does not. All right, and then noticing here the two different shapes of the graph that it's going to make. Okay, and then here's a couple examples of trying to figure it out. So if you're given the width and the height, again, you can just plug in and solve for the constant. Or if you're given one variable and the constant, you can solve for your missing variable. Okay. Lastly here, a couple reminders for the checkup. Okay, a couple of reminders for the checkup. Using the graph, find the constant in the equation. Okay, so you're just doing that for all of these problems. So again, pick any point. Pick any 2 points, or any point, your x and your y variable. Plug in. As long as you know that x is going to be your width and y is going to be your height. You can plug in and solve for your constant value there. All right. And a last minute reminder, you have a quiz. The quiz is mandatory. The practice is extra credit. Okay, the quiz is mandatory. The practice is extra credit if you would like. Okay. And then that's going to bring us to the end of today. Okay, that's going to bring us to the end of today. So we covered 1 through 4, 1.4 through 1.6. All right.